Well, so good morning to all of you. So, today we will be continuing our discussions on the estimation of void fraction as well as the frictional pressure gradient. So, in the last class what we did was we discussed that primarily this the approach to find out the frictional pressure gradient in absence of any further information, it is primarily empirical in nature. Okay. And the empirical correlations, they are mainly expressed in terms of two phase multipliers, which express the two phase pressure gradient in terms of known single phase pressure gradient quantities. They can be single phase pressure gradient when the liquid flows alone in the pipe, single phase pressure gradient when the gas flows alone in the pipe, or single phase pressure gradient when the entire mixture flows as a liquid or as gas in the pipe. So, these are the four ways in which rather four two phase multipliers with the help of which two phase frictional pressure gradient can be expressed in terms of equivalent single phase pressure gradient terms. The other thing which I discussed is, instead of phi LO square and phi LO square and phi GO square, please remember they are very useful for boiling condensation situations where maybe the liquid it enters at saturated or slightly lower than saturated conditions inside the pipe, and there is change of phase as it goes on. After this, what we discussed was that phi in the separated flow model we prefer to use phi L square and phi G square instead of phi LO square and phi GO square. We found that they conform to certain limiting conditions, and that is why we prefer that. And after that, what we did, we found out the graphical as well as the analytical correlations between phi L square and phi G square, the oldest and the most widely used correlation which has been proposed by Lockhart and Martinelli. So, the graphical correlation has been expressed in terms of the graph which I have shown in my transparency. This particular graph, it shows the graphical correlation between 1 by phi L square and 1 by phi G square, and then subsequently we derived the analytical expression, where the analytical expression it is of this particular form, and we find that the analytical expression takes up different forms or takes up different types depending upon whether the flow in the two phases are laminar or turbulent, and also for turbulent flow whether we use a Blochius type of equation or whether the turbulent flow is calculated on a mixing length basis. So, this mixing length basis was your home assignment yesterday. Achha, the other thing which, so after this the next thing which I was trying to do yesterday, I could not complete it. So, I will be doing that portion, and then we will be going into further discussions regarding the improvements of this particular correlation. Now, the problem of this correlation, as you can very well see, that both phi L square and phi G square, they contain the two phase pressure gradient term, isn't it? This is the unknown, this is the thing which you want to find out. So, therefore, in the your graphical expression, if both the x and y axis they contain the unknown parameter. So, naturally from here if you want to find out the two phase pressure gradient term, then you have to use a trial and error technique, isn't it, because both the x and y axis have got the unknown pressure gradient term. So, therefore, in order to avoid this, what are the different things we use, what are the other correlations, those things we will be discussing in the present class. But before we go to that, the thing which I had told you in the last class was the correlation was based on certain assumptions. If you remember the assumptions we had already discussed in the last class, the assumptions, the first one is fine. The only thing is that we assume that both of them flow in two separate cylinders such that the cross sectional area of the two cylinders equal to the pipe cross section. Now, remember one thing, even for stratified flow, if we can assume that well they are more or less cylindrical, but definitely in annular flow we cannot assume it. The liquid film cannot be assumed to flow in a cylinder. So, naturally if you have to take an equivalent cylinder for the annular flow case, then the shape factor has to be accounted for, isn't it. So, this is the assumption, or rather this is the anomaly in the assumption 1 which we have stated here. The next assumption was the two phases do not interact with each other. This was a very serious assumption, and that we will see shortly. In fact, I had started in the last class. I had tried to apply the separated flow model after deriving the analytical expression. What I tried to do is, I tried to find out phi L square for annular flow by considering the actual flow circumstances and by considering the Lockhart-Martinelli correlation, and I wanted to show you how well these two particular expressions they agree. I could not complete it today, I will be completing it. So, I would like to show you that there are some discrepancies in the separated flow model. It does not give us exactly the same results which we would get if we consider the actual flow characteristics, and we will be showing it using the annular flow situation, which is indeed a separated flow situation, but in this particular separated flow situation certain assumptions they do not hold. Well, the other assumptions they follow as a result of these assumptions. So, we will not be going into the details of this. Now, to continue with our discussions with the annular flow situation which we had used, or rather which we had started in the last class. So, I would just recollect what I had discussed in the last class before I proceed further. The first thing which I had got there was, I had obtained the thing which I did was, in the last class I had first discussed that how to, when we want a empirical or a graphical or an analytical expression for phi L square and phi g square. So, how to define these two? The phi L square, suppose you take, this is the frictional pressure gradient in the two phase condition as a ratio of the frictional pressure gradient when the liquid content of that particular mixture flows alone in the pipe. Now, based on the assumptions of Lockhart and Martinelli correlation, if you see assumption 3 which I have written down in the transparency, assumption 3 and assumption 4 which gives you this particular expression. So, based on this expression, the thing which I had written down in the last class was phi L square was minus dP dz frictional for the liquid portion of the flow divided by the frictional pressure gradient when that particular liquid flows alone in the pipe. So, based on this we had derived the frictional pressure gradient for the liquid portion, and then we had derived the frictional pressure gradient when that liquid flows alone in the pipe, and finally, from those expressions I had obtained expressions for phi L square, and I had said that a similar expression exists for phi g square as well. Now, if we consider this particular phi L square here, what do we get? By considering this particular phi L square, this was d L by d whole to the power n minus 5 gamma r whole to the power n minus 2. Okay. Now, in this particular case, what is d L or what is A L? The cross sectional area of the liquid occupied portion of the pipe. It is naturally gamma pi by 4 d L square. Agreed? This for d L it is the hydraulic diameter, it is nothing but 4 R h, where R h is the hydraulic radius, which is nothing but 4 into, you remember it very well, it is the wetted area divided by the wetted perimeter, is not it? So, therefore, what is the wetted area in the annular flow case? Suppose you take up the annular flow case, I had already drawn it in the last class. This is the gas code, this is the liquid film. So, what is the wetted area in this particular case and what is the wetted perimeter in this particular case? Sorry, dl equals to, I wanted to say that dl equals to 4 RH. Anyhow, sorry, so I just wrote it, yeah, it is all right now. So, what is the wetted perimeter in this particular case? What is it? Pi d delta, and wetted perimeter is equal to pi d. So, therefore, your 4 RH equals to 4 delta. Agreed? Well, so So, in this particular case this dl it can be substituted by 4 delta, fine. Okay. Now, what about this gamma? Okay. How to substitute gamma? Now, we know one thing, what is 1 minus alpha equals to? Alpha equals to a g by a, agreed. 1 minus alpha it should be a l by a, agreed. What is a l? I have already written it down. It is gamma pi by 4 d l square by pi by 4 d square, fine, or in other words this is gamma d l by whole square, agreed. So, what is gamma? The shape factor, this is equal to 1 minus alpha d by d l whole square, fine. Okay. Or in other words this can be written down as what is your so this, and so therefore, this is equal to 1 minus alpha d by d l whole square, agreed. And now, what is this 1 minus alpha equals to? It is nothing but d l by d whole square, and what is d l? 4 delta. Is it clear to you? See, what is 1 minus alpha? L by a, agreed. What is this L by a? This is nothing but, can you write it down, just see what I am doing, pi d delta by pi d square by 4. Can you do it, yes or no? We can do it, isn't it? Try to understand, you can express it either in terms of dl or in terms of d and liquid film thickness delta, isn't it? dl is the hydraulic diameter of the liquid film. If you have to express it in terms of dl, then there has to be a shape factor, or in other words you, but this particular thing is based on the assumption that the liquid film thickness is much less as compared to the tube dimensions. And the things, the assumptions which I had told you in the last class, I do not know whether I have that particular slide or not, that the interface is completely smooth, it is much thin as compared to the tube dimensions. Under that conditions, from flat plate assumptions we can take d as your sorry, yeah, from that particular situation we can write 1 minus alpha, this is equal to a l by a, which is nothing but gamma pi by 4 d l square by pi by 4 d l square, or this can also be written down as pi d delta by pi d square by 4. Sorry, I should not have written it down here, isn't it? Can I write this? Agreed? If the liquid film thickness is much less as compared to tube dimensions, definitely 1 by alpha can be expressed in this particular form, yes or no? Yes. So, for what is this basically? This is 4 delta by d, yes or no? Agreed? And which is nothing but equal to d l by d, isn't it? So, therefore, what is d by d l equals to? From here what do we get? D by d l is nothing but 1 by 1 minus alpha, agreed. So, therefore, what is gamma then equal to? This gamma then this is equal to 1 minus alpha, and d by d l whole square means 1 minus alpha whole square. If you want me to repeat, I am going to repeat it once more. Is this portion clear to you? So, therefore, I have got gamma, I have got the expression of d l by d. Both of them I have got in terms of alpha, delta, etc. Alpha is the void fraction, delta is the liquid film thickness. This is the delta portion, okay, and the void fraction is alpha. So, therefore, from here what do I get then? From here I get this phi l square, I will write it down once more, this is d l by d whole to the power n minus 5 gamma to the power n minus 2. What is d l by d? It is nothing but 1 minus alpha whole to the power n minus 5, yes or no? Fine. And what is gamma? This is nothing but 1 by 1 minus alpha. So, therefore, this will become by 1 minus alpha whole to the power n minus 2. fine. So, therefore, this is nothing but equal to 1 by 1 minus alpha whole cube. Agreed. This we have obtained from separate cylinder model. So, from separate cylinder model, based on the assumptions, what were the assumptions? It was based that the two fluids flow in separate cylinders, where the cross sectional area of the cylinders add up to give us the cross sectional area of the pipe. Number 1, due to which what could we say? We could express AL in this particular form and A in this particular form. Number 1. What was the next assumption that we assumed? We assumed that this phi L square, it can be defined in terms of the frictional pressure gradient in the liquid portion divided by the frictional pressure gradient when that liquid flows alone in the pipe. Okay? And how did I take up the frictional pressure gradient in the liquid portion to be equal to the frictional pressure gradient in the two phase mixture? Because I have assumed that the two phases do not interact with one another. So, based on these assumptions, what did we get? We obtained phi L square as 1 by 1 minus alpha whole cube from the separate cylinder model. Now, let us see what we will be obtaining if we consider the homogeneous flow situation. Now, on considering the homogeneous flow situation, yesterday I had already started the derivations for the homogeneous flow situation. I had already started the derivation, yeah. So, in the last class I had already started the derivation of the homogeneous flow situation, where I had written down the assumptions that are quite justified, I should say. Entire liquid flowing as a symmetrical annular film, and there is a smooth interface between film and gas core. Had these assumptions not been applicable, we could not have written AL as pi d delta, is not it? And of course, it is a horizontal pipe, so the gravitational pressure gradient is not there. So, from this particular case, what we did? We performed a force balance on the combined phase and we obtained this particular expression. Okay, it was just the wall shear stress, we tried to relate it with the frictional pressure gradient, we tried to relate it with the pressure gradient, where the pressure gradient here is predominantly frictional in nature. It is a air water case that we have considered, where there is no change of phase, no gravitational pressure gradient, nothing for that matter. Then what we did? We tried to perform the force balance on the gas phase, gas portion alone. From the gas portion alone, if we just consider, then in that case we obtain the, instead of this expression, we obtain this expression, where d minus 2 delta is the effective diameter of the gas core. It can be taken as dg for that matter, is not it? So, accordingly we have written down the gas phase, or rather we have obtained the expression for minus dp dz f, the gas portion in this particular case. Now, remember one thing, after that what we did, suppose we would assume, see we want to find out phi L square. So, what is phi L square? Phi L square is nothing but two phase frictional pressure gradient divided by the pressure gradient when only liquid flows in the pipe. So, for finding out phi L square, we have to find out the pressure gradient when only this liquid flows in the pipe. Okay? And what is the pressure gradient when the two phase mixture flows in the pipe? That can be taken to be equal to the frictional pressure gradient when in the gas core or in the liquid film. So, in this particular case, we have taken it to be in the gas portion. Agreed? Well, anything if you don't understand, just tell me to repeat the whole that particular part. Okay? Anything which you don't understand. So, after that, once we have found out minus dp dz f tp, so after that the next thing was to find out minus dp dz when frictional pressure gradient when the liquid portion of the liquid film flows alone in the pipe. That was nothing but this, is not it? And then phi L square, it could be expressed as tau w Tp by tau w L, yes or no? Fine. Now, what is this tau w Tp? It is in terms of frictional pressure gradient, we can write it down in this particular part, where we find that the wall shear stress for the two phase situation, that depends on the velocity of the liquid portion, and in this case it depends upon the velocity when that liquid is flowing alone in the pipe, or in other words, if that liquid has to flow alone in the pipe, then the velocity which it would have is nothing but the volumetric flux or the superficial velocity, which is nothing but q L by A, Agreed. So, therefore, we find that u liquid portion by u L, this is nothing but u liquid portion by J liquid portion, yes or no? And then for do we know? We know J, the volumetric flux into area, is nothing but u L by A L. Do we know this? Or in other words, your u L by J L, this is nothing but A by A L, yes. And what is this A by A L? This is nothing but 1 by 1 minus alpha. Everything fit, see, if you remember, if you notice one thing, whatever I am trying to derive, everything is already available, you have already studied in single phase hydrodynamics, and certain very basic definitions which we have done. All the derivations are based on just these two things. If your single phase hydrodynamics concepts are clear, if you remember the new nomenclatures which we have defined, that to the very basic nomenclatures like void fraction, okay, and mass quality, then probably all the derivations you can make. The only thing which you have to keep in mind is that you should not make mistakes and you should not confuse between what you are doing. Whether you are finding out the pressure gradient when liquid flows alone in the pipe, whether you are finding the pressure gradient when that liquid flows as a film or as a separate layer in two phase flow, you have to keep these things in mind. Accordingly, you have to define the velocity, accordingly you have to define the diameter. If these things are done properly, then you will have no problems with two phase flow, and you will not think that there are too many nomenclatures, too many derivations and the calculations are long. They are long just because they involve more number of properties or more number of parameters as compared to single phase flows, but the concepts are essentially the same. So, if you see finding out your frictional pressure gradient or the wall shear stress, the expressions which you have used, you already know them from your single phase equations. Nothing new I am doing, but you have to keep in mind exactly what you are trying to do and use consistent things. If you are finding out the velocity of the liquid portion, keep in mind that this velocity will be equal to the Q liquid divided by A L. If that liquid flows alone in the pipe, it will be equal to QL by the total cross sectional area. So, these small things you have to remember. So, therefore, from here what did we get? We found out that U liquid portion by UL was nothing but 1 by 1 minus alpha, fine. Now, if we want to find out phi L square for the actual annular flow situation, then in that case it is nothing but FTP by FL into U liquid portion by J liquid portion, agreed, or FTP by FL into 1 by 1 minus alpha whole square. Till this portion, do you have any doubts? You tell me. Yeah.
What is the flow situation in annular or homogeneous?
Annular, strictly annular. Why do you think it is homogeneous? Where did this homogeneous thing come? You tell me. Louder. No, I did not mention homogeneous at all. It was exclusively, I first mentioned this separated flow model, the Lockhart and Martinelli correlation. Okay. So, thing which I did was, this is what I want to show you is how accurate the Lockhart-Martinelli or the separate cylinder model is. So, for that I took up a truly separated flow situation. What situation did I take? An annular flow situation in a horizontal pipe, where there is no phase change, a uniform diameter of the horizontal pipe, and it is it comprises of a very narrow liquid film and the interface is smooth. An idealized annular flow situation where the entire liquid flows as a film and the entire gas flows as a core. Agreed? For this particular situation, I applied the Lockhart-Martinelli correlation in this particular case, and I tried to find out phi L square from the Lockhart-Martinelli correlation. And what did I get? I obtained phi L square is equal to 1 by 1 minus alpha whole cube, fine. Now, I wanted to take up the actual flow situation and I tried to find out phi L square from here, fine. So, for finding out phi L square, what do I need? I need the frictional pressure gradient in the liquid portion or in the gas portion or in the two phase mixture divided by the frictional pressure gradient when that particular liquid flows alone in the pipe. Agreed. So, therefore, what did I get? I obtained from this entire derivation phi L square to be FTP into FL into 1 by 1 minus alpha whole square. This has nothing to do with homogeneous, mind it. Okay, it is simply a separated flow model. First, I tried to find out phi L square using the separate cylinder model as proposed by Lockhart and Martinelli. Then I tried to find out phi L square from the actual flow situation. Agreed. So, therefore, what did I get in this particular case? It is FTP by FL into 1 by 1 minus alpha whole square. Agreed. Now, in this case you try to observe something. Now, this FTP, or in other words, if we start from a slightly, or rather here also, this FTP or this tau WTTP, it arises why? Because the liquid film is in contact with the wall. Agreed. So, therefore, this must depend on what? Any friction factor depends on Reynolds number. So, therefore, this will depend upon the Reynolds number of what? Of the liquid film. It will depend upon the Reynolds number of the liquid film, yes or no, and this FL will depend upon that liquid flowing alone in the pipe. What is the difference between Reynolds number when liquid flows as a film and when liquid flows in the whole pipe? Basically, the velocities will be different, the hydraulic diameters are going to be different. Agreed. So, therefore, this FTP, this is a function of your film Reynolds number. And what is this film Reynolds number? This is, just see, it is 4 delta, which is nothing but dl. Okay? U film rho liquid by mu liquid. Do you agree with me? Do you agree with me? And what is this FL equal to? FL, it is a function of REL, so this is equal to D, if I take it as JL rho L by mu L, yes or no? Now, in this particular case, what do I get? So, therefore, I know FTP by FL, this will be a function of, just a function of, I will not write the details, 4 delta U film by D J film, JF or J film, whatever you write down. Yes or no? Do you agree with me? Achha, now we know what? We know U film equals to J film by 1 minus alpha. Do we know this? Fine, we know this. And next, what else do we know? We know from there 4 delta was equal to dl, that we have just derived, which is nothing but equal to d into 1 minus alpha, is not it? Just, in fact, I think 1 or 2 slides back only I had derived this particular situation. Here I had derived it, that yeah, 1 minus alpha equals to 4 delta, somewhere I had derived, I do not find it now. Here only I had derived it, dl equals to 4 delta, just now I have derived it. Okay. So, therefore, so from these two things, what do we find? We find that then RE film, this is equal to 4 delta U film rho L by mu L. So, instead of this 4 delta, I can write d into 1 minus alpha, and instead of this U film, I can write J film by 1 minus alpha rho L by mu L. Can I write this, yes or no? Can I write 4 delta as d into 1 minus alpha, U film as J film by 1 minus alpha? No problem. So, therefore, what does this reduce to? D J film rho L by mu L, is not it, which is nothing but equal to RE, your liquid when only liquid flows through the REL, when the entire liquid flows in the pipe, you compare this expression and this expression. Agreed? So, therefore, from this what do I get? I get that FTP equals to FL. For this special situation of annular flow, horizontal pipes, liquid film very thin, smooth interface, for these particular considerations what do I get? I find out that the Reynolds number for the liquid film interestingly is equal to the Reynolds number when that particular liquid flows alone in the pipe. As a result of which I can express your FTP is equal to FL. Fine. And therefore, what is phi L square then from this for this annular flow case? It is 1 by 1 minus alpha whole square. Do you get my point? So, therefore, from this what did I get? I obtained phi L square as 1 by 1 minus alpha whole cube, but in reality by considering the annular flow situation, in reality from the annular flow situation we obtain phi L square equals to 1 by 1 minus alpha whole square. So, this particular contradiction, this tells us why, or rather where these two cases they do not tally, and this particular discrepancy, this primarily occurs because we have not considered the interaction between the two phases. Since we have not considered the interaction, what was the basic thing that we could take? The frictional pressure gradient in the gas core is equal to the frictional pressure gradient in the total two phase mixture. This was the first thing that we had considered, if you see here. Okay. So, therefore, primarily the main reason for this particular discrepancy, it arose because we neglected the interaction between the two phases. Okay. So, therefore, what I want to emphasize is that this is not a foolproof correlation, but this has been tested extensively with a large number of data. This was proposed in the 1944-45 that particular regime. From then on, more or less lot of modifications of this particular correlation has been proposed, but more or less some sort of form has been maintained, and the main reason for this is that it is extensively used, and within reasonable limits it gives us a proper estimate of the frictional pressure gradient. But when you are using this, remember that there are certain assumptions, out of which the most severe assumption is that the two phases do not interact with one another, because that implies that one phase is not aware of the presence of the other phase. So, in that case it is almost similar to say that two single phase flow situations are occurring, but the basic definition of two phase flow is interacting flow of two phases. So, there the problem lies, but otherwise more or less we can use this. Okay. So, this was the thing which I wanted to show you. Now, we will come back to our Lockhart and Martinelli expression, and we will try to see what other modifications has been proposed, and accordingly we will be proceeding. Now, the first thing, if you notice, for this Lockhart and Martinelli correlation, we find that this gives us a correlation between phi L square and phi G square. Okay. What if you remember the basic definitions, I do not know whether I have the definitions here, I do not think I have them here. The basic definitions, I will just write it down once more. The basic definitions was phi L square was minus dP dz frictional two phase by minus dP dz frictional when that liquid portion flows alone in the pipe. Phi G square was minus dP dz frictional two phase divided by minus dP dz frictional when the gas phase flows alone in the pipe. I tried to derive a correlation between 1 by phi G square and 1 by phi L square. So, therefore, I want to do this just to find out the frictional pressure gradient. Now, we find that both in the y axis as well as in the x axis we have this particular unknown. So, therefore, if you have to find out frictional pressure gradient from this particular correlation, be it analytical, be it graphical, then it has to involve a trial and error technique, is not it? There is an unknown both in the x as well as the y axis, right. So, just to eliminate that particular problem, what researchers have tried to do, they have defined, or rather they have divided phi L square by phi g square. Once you divide this, what happens? This is simply a ratio of what you tell me? This is this mere, sorry, it is phi g square by phi L square. So, this basically becomes a ratio of minus dP dz frictional when the liquid flows alone in the pipe, and this is minus dP dz frictional when gas flows alone in the pipe. So, this becomes a known quantity. Okay. So, now if phi L square or phi g square is plotted as a function of this particular ratio, then if this is the x axis, then we know the x axis already, we can calculate it. Once we know this, then we can go to calculate phi L square or phi g square, whatever is there in the y axis, is not it, and we can find out frictional pressure gradient in a much more simpler fashion. So, this ratio it is denoted as capital X square. Please remember, do not write it as small x, because small x gives you mass quality, and this is the Lockhart-Martinelli parameter as it is said, this is the capital X. Make it in a very bold capital, so that you yourself do not confuse it with quality. Remember this. Okay. So, the next attempt which was done was to plot your phi L square phi g square, either it is phi L square or it can be phi g square as a function of x square. So, therefore, what we have, we can find out x square, moment we can find out x square, the curves are there, we can find out phi L square, moment we can find out phi L square, we know dP dz F L. So, we can find out the frictional, the two phase frictional pressure gradient. Clear to all of you? So, therefore, the next attempts were made to correlate not phi L square and phi g square, but to correlate phi L square or phi g square with x square, where x square is known as the Lockhart-Martinelli parameter. Agreed. So, therefore, the graphical correlation I already have, this is the graphical correlation. If you see, this correlates phi L square, this should be x square actually, this correlates phi L square with x square, these are the graphs here. Now, remember here, if you notice properly, we have 4 sets of curves. Why? Because one considers, I think they are very, the writings are very small, anyhow I will just mention them. One considers both phases in laminar flow, other considers both phases in turbulent flow, and in between they consider one phase is in laminar and the other phase is in turbulent. So, depending upon the 4 situations, we have 4 different curves. These are for phi L square and these are for phi g square. Okay. So, these are the different graphical curves. So, now your situation becomes much more simpler. You know x square, you can find it out x square, you know whether the liquid and the gas are flowing in laminar or turbulent flow. Accordingly, you select one particular curve from this family of curves and then from there you come to the y axis, you find out phi L square or phi g square, whichever you are required to find out. From there you find out the frictional pressure gradient. So, this is the actual situation which is usually used or which is usually done in this particular case. Okay. So, in this particular case, what is this x square? This x square, this is slightly wrongly written, this should be liquid. It has been wrongly written as tau, but it is actually L. Okay. So, therefore, this x square by definition it gives a measure of the degree to which the two phase mixture behaves as a gas rather behaves as a liquid rather than the gas. It is basically the frictional pressure gradient, the ratio of frictional pressure gradient between that of the liquid and the gas, or rather so it gives you the degree to which the two phase mixture behaves as a liquid rather than a gas. So, this is the basic definition. Now, remember, and this particular correlation which I have shown you, this particular correlation it has been verified with a large number of experimental data. Okay. And then it was also felt that if the frictional pressure gradient can be correlated with x, there should also exist a relationship between void fraction and x as well. So, the void fraction was next plotted as a function of x. I have shown in many textbooks you will find that there are different sets of curves for phi L square. In fact, Wallis, if you see, you will find that they have given 4 sets of curves for both phases in laminar, both phases in turbulent and so on and so forth, but here I have condensed everything, so that it is easier from one particular graph you can get all the information. Okay. So, here you find that if we plot alpha versus x square or 1 minus alpha versus x square in this particular graph that I have drawn, you find that in this particular case, interestingly, for all the 4 cases, if you see this the transparency or the presentation which I have prepared here, in this particular presentation if you see, we find that while in phi L square versus x, you have 4 separate curves for laminar, turbulent, laminar, turbulent, these particular cases. Here we have one particular graph. This is the graph of 1 minus alpha and this is the graph for alpha versus x square. So, in this particular case we find that this the relationship between alpha and x square, this is independent of flow patterns, independent of the way the 2 phases flow when they are alone in the pipe. Okay. And this particular expression which I have drawn here, this can be mathematically represented by the analytical expression which I have shown here. I do not know whether it is evident or not. So, I will be writing down the analytical expression. It is alpha equals to 1 plus x to the power 0.8 whole to the power minus 0.378. Okay. So, therefore, this was the analytical expression. Okay. Now, remember certain things, the things are out of these particular 4 curves that I have shown here. In this case, it is very rare that the gas flowing alone will be turbulent and the liquid flowing alone will be laminar. So, therefore, this case is not but much used, but this particular curve can be used, and we find that the curve, it gives you a comprehensive idea about how phi L square and alpha vary with x square. So, from this one curve, if you can calculate x square, you can calculate phi L square, you can calculate alpha. Moment you can calculate both these equations or both these particular quantities, we can go to the mixture momentum equation which we had derived for 2 phase separated flow. There were only 2 unknowns there, if you remember. If you see that expression, one was the frictional pressure gradient and the another was the alpha. If we can calculate alpha, we can calculate the gravitational pressure gradient. If we can calculate your frictional pressure gradient, then from these 2 quantities you can calculate each and every individual terms which were there in the mixture momentum equation, which was used for calculating the pressure gradient when 2 phases are flowing under separated flow conditions. Okay. Now, you just remember certain things. The things are that this particular correlation which I have shown you, this is used specifically for horizontal flow without phase change. So, therefore, it is more preferable for air water, for steam water flows. It has not been derived, it has not been derived for that particular situation. So, the correlation was specifically derived for horizontal flow without phase change or significant acceleration, and it can be used to calculate both the void fraction and the pre-frictional pressure drop, even when these effects are not negligible also. It can be used. Okay. When we have some amount of acceleration pressure drop, under that circumstance also it can be used, but remember one thing, the more important the other components of pressure drop become, the less important frictional component of the pressure drop becomes, the more inaccurate the correlation becomes, because the basic thing was based on the fact that the 2 phase pressure drop primarily comprised of the frictional gradient. So, moment that is violated, the resulting error becomes more. But very frequently what people do, they find out the frictional pressure gradient from here and accordingly they calculate the gravitational acceleration and they can calculate the total pressure gradient. That is also done for this particular case, and we find that the correlation which I have shown you graphically here, this in essence it balances the frictional shear stress versus the pressure drop. this particular graph. Okay. But the only thing which we have to remember in this particular case is that more or less number of workers have also found out that the two phase frictional multipliers, this phi L square and phi g square, they can be correlated uniquely as a parameter, as a function of this particular parameter x, okay, where x was defined in the way that I have already mentioned. This gives you a measure of the degree to which the two phase mixture behaves as a liquid rather than as a gas. Okay. Now, subsequently a large number of other modifications were suggested. What was the first modification? First modification was, if an analytical expression can be proposed which would condense these curves into equations, that would be very useful. And subsequently people have tried to find out the analytical expressions, and I have written down the analytical expressions on the side of the graphs. If it's visible to you, I do not know. It's phi L square equals to 1 plus c by x plus 1 by x square, and phi g square equals to 1 plus x square, okay, where the value of c takes on different values for these are the corrected expression. This was, sorry, this should have been c x. So, these are the corrected expressions. If you want, you can take them down, where we find the value of c is different for different types of flow of liquid and gas when they flow alone in the pipe. Okay. In fact, the turbulent spelling is also wrong here. So, those things, since you are masters of fluid mechanics, you are doing multiphase flow, advanced fluid dynamics, this should not be a problem for you. So, we find that the value of c is 20 when both liquid and gas are turbulent, the value of c is 12 when liquid laminar, gas turbulent, c is 10 when liquid turbulent, gas is laminar, and so on and so forth. It goes on in this particular case. Okay. And one more has been missed out, c is 5, you can note it down, c is 5 when both liquid and gas are laminar. That has been missed out here, you can just note it down. Remember one more thing also, that these particular correlations have been derived for two phase two component systems at in horizontal flow at low pressure close to atmospheric pressure, isn't it? They have been derived under that condition also. So, its application to situations outside this range of consideration is not recommended. Okay. So, remember this part also. So, therefore, but these things have to be considered. In the next class, we will be dealing with certain generalized or certain modifications, certain improvements of this particular correlation, and that will finish off our separated flow model. Thank you very much.